Okay, this is the last one in the little three-parter. This is on adaptive control. I've done feedback linearization already, I've done robust already. Adaptive is different because the assumptions that we make are different, and the assumptions that we have to make for adaptive control is that we have a system with unknown parameters, but these unknown parameters are constant, and it will become clear why that is the case later on. So I'm going to jump right into it with this first order example. I will probably do a second order example if I have enough time, but anyway, first order example, let's start. The first thing we want to do is define our error dynamics. So what is our error? Well, our state is x, so our error will be state x minus our desired trajectory of x, or desired value of x, xd. That's good, that's a good place to start. And now what we can do is we can take the first derivative of our error. So that's going to look like this. It's going to look like e dot, and that's obviously going to be equal to x dot plus, minus xd dot, like so. And you'll notice that actually we have an equation where we can get it in terms of x dot. I'm going to make a bit more of an intuitive step here, and rather than solve for x dot, I'm going to solve for a0 x dot, because it saves me having to divide everything by a0. And what that means is our error dynamics become a0 e dot. So that'll be clear. So if it's a0 e dot, then multiply everything by a0, and it's going to become a0 x dot minus a0 xd dot. Cool. And now we can just solve for a0 x dot, so let's do that here. a0 x dot is equal to minus a1x plus u. Great. And now it's the classic case of designing our controller u. We have to consider the dynamics that we want to try and cancel out, so in this case a1x, and we also need to consider that actually we're going to substitute it into this e dot equation, so we're also going to want to try and cancel out an a0 xd dot. So let's do this. I'm going to call it u hat. It's a guess at our controller. We want to do positive a1x, right? That would cancel out minus a1x. Cool. And then when we substitute it in here, we also want to add a0 xd dot to try and cancel out those dynamics. But remember, we don't know a1 and we don't know a0. These are unknown constants. So what we have to do is we have to basically take an approximation, a guess, and that's called a0 and a1 hat, like so. At this point, if you substituted these dynamics in and you knew a1 and knew a0, your closed loop dynamics would be equal to 0. But we don't necessarily want it to be equal to 0. We want to be able to prove that it's AS, asymptotically stable, and to do this we need to add some sort of controller gain to it, so we can make the system negative definite rather than just equal to 0. So what I'm going to do, remember we're working with error dynamics, not a sliding surface, so it's E, and I'm just going to call it K0 E. And you're welcome to add K1 E dot and so on. There's not really any point though, because it's a first order system. So that's going to be my controller for now. Now let's quickly note down something. I'm going to start using this thing, I'm going to call it a0 tilde, and this is going to be the real value of a0, which we don't know, minus our approximate of a0, which is a0 hat, and exactly the same for a1. So let me quickly change these to ones. And you'll see why this is handy, because now we're going to substitute u hat into our equation. So from the beginning, a0 e dot is equal to, let's substitute a0 x dot, minus a1 x plus u, let's have a look at what u is, plus a1 hat x plus a0 hat, let's do hat, a0 hat xd dot minus, actually I'm going to group the a0 terms, so let's not forget the a0 term up here, a0 xd dot, like so, and then subtract this term that I've left out earlier, k0e. This is a0e dot, and what we can do using this tilde notation is we can simplify it down a little bit. So a0 e dot is equal to, if it's minus a1 plus a1 hat, it's actually going to be minus a1 tilde x, and exactly the same for a0, minus a0 tilde xd dot, like so. That's our a1 and our a0 terms grouped, and then we still have to remember we have this k0e left out the outside. Cool. Now, for adaptive control, the next stage, really to try and identify our adaptive laws, is to define a valid Lyapunov function, and this, in this case, is going to be a0e, and we can understand why, because when we take the first derivative, we're going to get a0e dot, which we have, so we can substitute it in. So a0e is going to be in there, and we shouldn't forget 1 over 2, and then squared. Basically, that's almost it. We just need to add. This is where it differs from robust. We can't just work it out and then go back and find out what we need to do. I mean, you technically can, but it's easier just to remember. We also need to add 1 over 2 gamma, and then that's multiplied by all of your unknown terms, the tilde version. So a1 tilde. Actually, I'm going to make it in ascending order. So that one's going to be a1 tilde, and this one's going to be a0. Like so. And now let's take the first derivative. It's going to be a0 e dot e, great, plus, I'm going to separate them out now, 1 over gamma, it gets a little bit tedious here, tilde a0 dot tilde a0, like that, and this is the same, so I'm just going to copy it, but just for a1, like that. So this is our first derivative of the Lyapunov function. We can substitute in those dynamics, so I'm going to more or less copy this, substitute in a0 e dot, which we already have. So here where I've written a0 e dot, I'm just going to get rid of it and put some brackets in, so everything's multiplied by e, so we don't forget. And a0 e dot, again, I'm going to copy this because I am lazy. So inside these brackets goes a0 e dot, and we can instantly see that what happens is left over, which is great, we have minus k0 e squared, which is just k0 e times e, and then we also have minus a1 tilde xe minus a0 tilde xd dot e, and the stuff on the outside is just the same. Give me 1 second. Yeah, sorry, I had a phone call. Right, so what we can do is just quickly copy these from before and paste them back in here. So what we can see is actually we have A1 tilde and A1 tilde and A0 tilde and A0 tilde. So we can group these terms, and it will be this. V dot is equal to K0 E dot minus, actually I'm going to do plus. I mean, it doesn't matter as long as you pay attention to the thing. Positive A1 tilde is going to be in terms of 1 over gamma dot tilde A1, and then it's going to be subtract xe, like that. And same for A0. What I can do is save a teeny bit of time maybe by copying that. It's going to be 1 over gamma A0, but it's not xe, it's xd dot e, like that. This is great because now what we can do through the definition of, well, through this definition I suppose I should say, we have A tilde is equal to A minus A hat. So I think I've done this already up here. Here. And what happens is when we take the first derivative of this, it's going to be is equal to dot minus dot hat A. A is just, I'm just using A, so I don't have to write A1 and A0 because it applies to both of them. And if you remember that A in this case is constant, right? So A dot is going to be 0. So basically all it leaves us is, where's this closed brace? I don't know. Fine. What it leaves us is A tilde, actually A dot tilde, is equal to minus A hat dot, which is good because A hat dot is a guess that we made, so that's something that we can control. And this is where the so-called adaptive law comes into place. If A hat dot is something that we can control, and that's equal to A tilde dot. We have A tilde dot and A0 and A1 tilde dot, so we can substitute this in for minus A hat dot. Design A hat dot as an adaptive law to cancel out the dynamics xe and minus xd dot e, and what that lets us do is basically cancel out these whole brackets, make these brackets inside these brackets equal to 0. It just gets rid of all mention of A1 and A0, just leaves us with a K0 E dot, which is fully in our control, and that's our control again, and we can prove asymptotic stability. So the way that I would do this is I would say, okay, A1 hat dot is equal to, well, let's look at the dynamics. If I wanted to make this bracket 0, it would need to be equal to gamma to cancel out the 1 over gamma, and then positive xe. So xe, which is fine, but note that actually A tilde dot is equal to minus A hat dot. So all I do here is put minus sign. Just don't forget this sign change. I basically left out the sign change and done it right at the last minute. You can do it whenever, but do remember to do it. Same for A0, but slightly different dynamics. A0 hat dot is equal to gamma again, to get rid of the 1 over gamma, and then dot xde, and don't forget the minus sign. And what this will do is it will basically give us v dot is equal to minus k0 e squared. I've just realised here I made a mistake there. That's not e dot, it's e squared. So that's it, and we can prove asymptotic stability with that. That's the first order example. I realise time's dragging, so I'm going to make this a 2-parter, potentially 3-parter if I do neural network. So I'm going to end it here, but that's how you do first order adaptive control, and that's I've showed you how to design the adaptive laws and why they work and what it leaves us with. So there we go, all done.